Well, actually, wait, no, I was in last spring.
Yeah, oh, yeah, I was in spring.
No, last spring? Even this spring, there was like 5 years.
But he like, he just last said,
Google,
a year ago. Yeah, he does look real. Really? I had priors.
You have to like 40 pages of this.
Yeah, literally. Yeah, we did. And some of them had writing on it. Like one line had like it was highlighted. Like where the end we had it was like a robot that had to go there like hit the wall.
I need 5 electives.
I think most of them easier than that.
Huh? What's the better one? Is it anything like 362? It's way better. It's the next one. But you don't actually.
No, I need to get in there.
But like half of the people do that crap, the crap is in C, and so
It's all in C. Oh, it's in C? I like C. I can understand C.
If you could get used to looking at data sheets.
Well, we need to cover several different topics today. So we need to finish what we left in chapter 5, the bivariate Gaussian. So it is also called joint Gaussian random variable, joint Gaussian distribution, or bivariate Gaussian distribution. And we need to cover the example we haven't finished in chapter 6, functions of 2 random variables. And I will point a little bit here. There is one theorem I didn't talk yesterday. And we'll try to go through 9.1. We did 9.1 yesterday. Expected value of the sum, if you still remember.
no.
We'll go over first. So the new thing here, we need to talk the moment generation function today. And there's several different concepts. It's like basically what we left for chapter 5, and some very good example in chapter 6 and chapter 9. But we cannot finish chapter 9. We just mainly talk about the most moment generation function. So we'll go a little bit fast. I will try to be fast. Some of the concepts you need to know. You're required to know the concept. And so if I give you like table or the moment generating function, then you need to be able to use that. But you're not required to derive or do the proof. Okay? So one example we did yesterday, Dr. King asked me to continue on this. If you still remember, we talked about the max and min of x, y. So it's 2 random variables, x and y, but you have another function. Most easy case is w equals x plus y. And you can see all kinds of different functions. Those are very popular functions, and you need to be able to do a problem like that. So this is the max value of x and y, and you know the possible region for x and y is from 0 to 1, 0 to 1 for x, and both x and y. So this case we did yesterday. If you think about the max of x and y, this line is x equals to y. So above this line, anything above this line is y greater than x. Anything below this line is x greater than y, right? Because you go this way or you go that way. So when x is greater than y, x must be the maximum of those two larger one, and y is the smaller one. So you have only one bound here, but it will generate two different limits for both x and y, right? So x has to be less than this limit. Also, because y is less than x, so it has to be. So both of them is limited by this number, right? If x is less than y, you are in the lower part here, then y is the larger one, so it's less than 1/2. But also same thing, x is less than y, so x has to satisfy this at the same time. So think about that. Those conditions, max of x and y is less than certain value, means both of them need to be less than certain value, right? So I have to give you a square region. Of course, you're using same limit to limit both random variables, right? So that's why you get this. You cannot get a rectangular because you have the same limit for both x and y, right? If you're asking the mean of x and y, if we do from this way, you think like this. Anything below this line, if x is greater than y, means y is the mean of x, y. So y has to be less than 1/2. There's no limit on x, so x can go this way, right? Because only one limit on the minimum, so it can be, but because x is greater than y, so it's anything here, no there, right? So this part, consider everything above this line. Then the minimum is x less than 1/2, so you're bounded to this part and above this line, so you go that way. Can be everything here. If you think about this, it's not taking the intersection. This one is taking intersection. What does intersection mean here? It means both x and y need to satisfy this. Here, either y or x need to satisfy this limit. Means you're taking a union. It's an or relation here. It's an and relation here. So you have to be bigger, right? Bigger area, because it's more different cases here. Your x can be the minimum, your y can be the minimum. So either x is limited or y is limited, but you don't have any limitation on the other part, right? So you draw, if I draw it, by the way, I scanned this and put it on. I haven't put it online, but I will do that tonight. So you don't need to worry about no. It will be this region, right? So this is less than minimum value or maximum value, less than certain limit. How about greater than? If you just look at this figure, you know if I change this to greater than 1/2, it has to be the complementary part of my square, right? So it's that part, right? So you need to be able to do all kinds of problems like this. Okay? Any questions? Question? Okay, make sure. Then this is the other problem we haven't finished yesterday. So the density function for joint probability density function here is a constant value 1 over 3. So basically your area is a rectangular and the height is constant at any point in this, right? Define a function w equals x plus y is the sum of x plus x and y. If you are asked to calculate the probability density function for w, we need to analyze step by step if you still remember. So common way to do this kind of problem, for any random variable, you know the joint probability density function, and you are asked the probability density function for the function of x and y. So one way to do it is you first find CDF of this function w and do derivative, get the density function little f. Okay. Another way, you use this relationship. This is the joint function, so it means it's in 2 dimensions. But if I substitute in, use this, for example, my w is x plus y, that means I can represent x and y, use w, and the other random variable. I can only left one random variable. So this will reduce the dimension. It's the same method, and we'll do the example, then you will see. Integrate your density function through certain direction, and of course you want to represent one random variable, use w, okay, and you get rid of the other random variable by integrate through all possible values, right? Because there's only w and x here. If I get rid of x, then it will result in only function only about w. Here, same thing. If I get rid of y, I integrate through all y, so I will get rid of y, then it will give me a function of only w, right? So it's same thing. Here is from density function to density function, or you first find probability, which is your distribution function, and then do derivative, you find the density function, right? First, it's obvious or to think about the probability. So the first case, you need to analyze x and y. X can take 0 to 1, y can take 0 to 3. Then your greatest value for w is 4, and smallest value is 0. And the line w equals x plus y, which is y, the slope is -1, and intersect with y-axis at w, right? You know this length is w, this length is w2, I think. Yes. Of course, it's -1 slope, so it goes this way. When your w is greater and greater and greater, it goes this way, right? Of course, you have a 1 slope, so this side is same, just through this direction, right? And your w is this part. You only have possible values or positive density function here. So if I go here or here, You don't need to analyze because it's 0 there, right? So first case, W is less than 1. Why it's less than 1? Because if you think your W is increasing like this, when you get here, your W equals 1, right? This is the point. But if I go further, here is my W is increasing, increasing, increasing. You find all these lines, if I pass this 1, and before this 3, all these lines have same length there, right? But this line is increasing, increasing, increasing until I get 1, right? Right? Okay.
So you wouldn't integrate from, in terms of x,
Yep.
maybe from...
Yeah, you can use any direction. We'll do that right now. Okay. So we are thinking about probability. For different cases, my W can increase like this, right? And we think about different cases, the probability of different cases, which is cumulating the density function, right? So you have to do integration because you're accumulating your density function. The only thing you need to decide is from where to where for your x and y, right? So here, if you think this way, my x is starting from 0, right? But my x can end here, and here, and here, or end here, right? But it has to be on that line, and that line is W is x plus y. So the x value on this line, for example, this dot, is your current W minus 1, is it? Whenever I fix one line, means my W is fixed. For example, this red line. Then the x value, any x value on this line is W minus 1, right? So, okay, you decide x is starting from 0 to this line, and this line is W minus 1. So you can get rid of x, so you do the integration through x. And then you need to think about the vertical direction. You go this way, because you have already represented this, so you don't need to worry about this. You only need to worry about this direction. It goes to 0, from 0 to maximum value is W, right? My W can be here, can be here, can be here. But it is always from 0 to W, right? For your y. So I decided, if you do another way, this is W equals x plus y, means if I carry my x is W minus y, I carry my y is W minus x, right? So just now I did this way first, dx first, then dy. If I want to dy dx, it means I need to think about this first and this second, right? So y is starting from 0, ending at this line. First, I think this first, I need to take care of this line. And that is W minus x, yes. And first, I have already represented it here. So for x, just start from 0 to, what's the value here?
1.
Yep, 1 might be there, right? So it's same thing. And you need to try this by yourself, and you will get W square root 6. When W takes second, past this 1, 1, then it increases to here, 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 until 3. After 3 is another case. Just look at that step by step. So
Could Could you go to the top and tell us what a real question is?
You forgot that?
What are we
The
solving for?
density function of W. So
And
we
that's
are
just
first solving the CVF for W and do derivative, right? So I don't want to do from here to here. Why? If I do that first, means I do dx first. Some part end here, some end here. That's two different representations, right? So I don't want that. It's two part of the integral, so I just do one. It's always starting from 0 to this line for my y, right? And then that line, you know, w minus x. You always represent y using the function. So dy here has to be w and x there. And you will generate some x function for this part. And then you do integration for x and get rid of x, right? And you have a function only for w. So it's always like that. When w passes 3, I don't know if you can.
Should we the same as the value before?
You're thinking this part, or what?
Yeah.
Great. Anyone know why he's
It'll be
pointing
up
on that?
up to the one value.
If my w takes value greater than 4, means I'm higher than that. It has to be 1. You know that, right? Cover all the possibilities, right? But now you need to write out the function, then distribution function. For w is greater than 3, less than 4. This part, right? So for example, w is what some value here between 3 and 4. It will intersect this, get this point and this point. And you know the slope of this line is 1. So it's very nice because this has the same length, right? And this has the same length. Same here. One thing you can do is integrate this area, but it looks a little bit complex. You can still do that. Another way is I like this little triangular. So I just use one, because remember you are accumulating the volume, right? So you have a height here, but the height is constant everywhere. So it's 1/3 there. Just use 1 minus the volume of this triangular or one part of your box, right? So I integrate, this is my head. From x from here to 3, because 3 is fixed, right? And my y is starting from this line to Yep, my x is starting from, you can do 2 different ways, but here what I did is x start from this line to 1, right? And y is this to 3. Y it is w minus 1, because, how can I draw it? Not good. You know this is 1. This is 1. This is 1. This is 1. This is 1, right? This is 1. This is w. So w minus 1 is this height, right? So this is W minus 1. And I do integration, I will get this. But actually, it's very tricky. You can even just don't do the integration. Just calculate the area. Because you know the height is a constant, right? So the area is 3 minus, this point is W minus 3. Give me this length here. And I know cos 45 degree. So this thing. Right? So I square this, divide by 2, which is my area, right? And my area times my height give me the volume, right? You will get exactly the same thing. So it's a little bit tricky, but you have many ways to do that. The basic thing you need to know, and first this problem is nice. You can have all kinds of different figure, different requirements, right? So you always do big FW and do the derivative, which is very safe way to solve this, right? So I have first case. By the way,
why would you do that third integral is so hard? Why wouldn't you just do the second integral and then take 1 minus your 2 integers added together?
there's no third integral, just 2 integrals, right? I'm just integrating something through.
That's the third set of your bounds. W between 3 and 4. There's 3 different cases.
Oh, you mean 3 different cases? Yes.
Right. So you know the total of it's going to be 1.
Yep.
And the first integral is easy. The second integral.
How you can decide the function? I know the value. You know what I mean? I know the area of this part, or the area of this part, or the area of this part. Fixed value I know, but I want the function, right? I'm not asking you certain points like that W takes 3, what's the probability? I ask you the function, right? Because you get this is your answer for W greater than 3 and less than 4, this is your answer. And if I put 4, if W takes value 4, it will give me what?
1.
Yep, you know that. So when W takes any value, it is the probability. This is your value, right? So you fix your W, you will get a probability. That's why we want this function, right? It represents everything. So it's much easier to calculate the volume, the space, the area, but we are doing another general form, right? So, and we saw the different functions here, here, here. I do the derivative with I'll get 1/3 W here, and constant value 1/3, and this give me 1/4. Sorry, 4/3, and this. So if you look at this, this is a constant value. Why? Because you are moving here to here, right? Your length of this line is constant, right? The length of this line is constant. And I times the length of that line by 1/3 will give me the volume of that certain line, which is my density, right? So it has to be constant. And this is a linear function of W.
Could you zoom out a little?
You should remember. For W through 1 and 3, it gives me a constant. This is the density. Because this line has a fixed length, and I always times this line to 1/3 will give me the probability. Because this length is fixed, so it has to be a constant value here. And you know the first case is your length of this line is increasing to here. And if I use 1, the biggest value of this part, it gives me this, which is exactly the starting point of my second part. So you can always verify that here, if w takes 1, it will give me 1 over 6. Then this start from 1, if w takes 1, it has to be 1 over 6. If they doesn't equal, then you make error, right? So
Could you go back to step 3 real quick? You said in the end problem, if you plug in 4, we get 1.
First, you are calculating the big F distribution function, and your distribution function for this part is starts from 3 to 4, right?
Yeah.
And if your W takes the biggest value, which is 4, that means you are here, right? So you covered all the possibilities. So you have to get 1 for the probability, right?
But
Which
if
is,
if you plug in 4, doesn't that equal 0?
you did this one, maybe, right?
Yeah.
But remember, we are using 1 minus this,
Oh, okay.
right? That's my small part, but this is this we want, right? You can check. This has to be 0 because there's 1 here, right? And another way, we have many examples on the book you can read through, is substituting my second random variable. You can change y or you can change x. Represent your x with the function and the other random variable, or represent y with the function and the other random variable. Then you only need to integrate through one dimension, right? You only need to integrate your density functions through x or through y. And think about that, you are actually trying to represent the density for one line. And you still have 3 different cases. I won't do this, and you need to do this by yourself. Try all possible cases. And there's a lot of different examples. And I think Dr. King introduced a couple yesterday, so we'll look at another one. Same, you have the joint density function, and you have a function of x, y, is y over x. You want to calculate your density function of your w. Then the first find big FW, which is the probability of big W less or equal than little w, right? And your big W is y over x. So it's same if I write it like this: PW less than little w equals probability y over x less than little w equals probability Py less than w times x, right? So you represent this with this. Now think about this. If you draw the figure out, every line here is y equals w times x, and your slope is w. And when you're changing your w, you're changing the slope of this line. Remember, there's no constant, there's no intersection, so you just intersect with 0 here. So it starts from 0 and just change the angle, right? And you want all the area which y less than w times x. So it can be here, 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 just within this, everything within this angle. Okay? So you're integrating x from 0, sorry, y from 0 to this line, and x is not fixed, right? So it's 0 to infinity. So you can do other examples on the book to get comfortable with this, and this is very important. I don't have enough time to do more examples. Very quickly talk a little about I learned yesterday. If x, y are independent, we just talked those yesterday, right? So you will have the joint probabilities, product of the marginal probability density, P, for discrete, density for continuous, right? And if they are independent, means knowing y or knowing x doesn't give you any information of this. So expected value of this condition on y or conditioning on x is same as the expected value of that random variable, okay? But that's no, you know they are independent. So what is E of expected value of x given y? Now this is given y for a fixed value, and what's the expected value of this? That means I need to get rid of all possible y. So this second expectation is for the y through all possible y, okay? And you know this. This is a conditional expected value, conditioning by y. So you need to recall that. Conditioning by y. So you have to use the conditional probability or conditional density, right? So that's here times x integrates through all x, and times the density for y. Then you will find this very nice because I move this part into here. It will give me this, which removes the uncertainty of y and give me the fx. And I have a little x outside, so it equals to G of x, right? So you are doing the first, you have the first expectation, but it's conditioning by y. And if you do the expectation for that again, it means you're getting rid of that y. It's just a leave only x there. This is very nice formula. Alright, we will start the bivariate Gaussian random variable. Maybe you can first look at the figure. We know one-dimensional Gaussian look like this, right? And if it's two-dimensional, this is figure for that. So it's like there's a peak at certain point, and you have different shapes. If this two have different mean value, different standard deviation, sigma and mu, right? We'll have all kinds of different figures. So it is also called joint Gaussian random variable. This is the general formula definition for bivariate Gaussian random variable or joint Gaussian random variable. It looks a little bit complex. You're not required to remember, but you need to be able to recognize it's bivariate Gaussian or not. So it turned out to be very nice because this rho here is the correlation coefficient of those two random variable x. Means if you have a joint Gaussian random variable, and if you calculate the marginal, and you know that many times from a joint to find the marginal, this will be a Gaussian, this will be a Gaussian, and so now after you know this nice property, you even don't need to do the calculation, which is from joint to marginal is if I get rid of x, I will dx integrate through all possible x, which will give me density of y or density of x through all possible y, right? So the joint is in this form, and the mu1, mu2 is the expected value of the x and y, and the sigma 1, sigma 2 is the standard deviation of x and y. You can prove this that you don't need to just try to convince you guys. If I do the marginal calculation, integrate through all possible y, it will give me this, which is exactly Gaussian random variable density function, right? And only for x here, left a part here. But this is integrating through all y, and you will recognize it's also Gaussian, okay? So if you integrate this density through all y, it will give you 1 here. So we'll left only this if I integrate through all y. And if you change x, y, it's the same thing. You integrate through all x, you will get a Gaussian density function for y, okay? And actually this part is the conditional density function. So everything conditional is in chapter 7, right? So it helps here. See, it's for fixed y value. The density of x looks like this, okay? For fixed y, the density of x. So it's a conditional density function conditioned by y. And the rho here is the correlation coefficient. So I assume we still remember what is correlation coefficient of x and y. What's here? Yes. Yep, great. And there's also a proof for that. If you feel interest, you can go through it. I'll just quickly tell you where. yours is chapter 7, right? Yes. By the definition of your correlation coefficient, which is covariance, upper part, right? And product of the standard deviation, lower part. Then, first, this is the expectation, so I just do the integration, because this is expectation, right? So, after my integration, I will get this, which is rho over sigma x squared, and this is exactly sigma squared. Sigma x squared will cancel, which gives me rho of xy. So this is the proof. Can go over if you feel interest. So it means in the bivariate Gaussian random variable, this is the general form of the density function. The rho here is actually the correlation coefficient of your x and y, okay, of your marginal. So if this rho equals 0, it will give you a very nice form, look like this. I want to compare. Rho equals 0, this 0, 1 disappear, 1 disappear, right? It will look like this. 2 sigma, 2 pi sigma, 1 sigma, 2 sigma, x sigma y, same here. And then this is exponential, so it's e to x squared over something, y squared over something. And you see there's 2 here. It's very similar to the Gaussian density function. You should be able to recognize those 4, okay? So this is very nice and used a lot. So we'll do one example.
If you're saying that they're independent, if you're saying that if they're independent, it's just 2 Gaussians multiplied together.
Well, I say it's rho is 0 means my correlation coefficient is 0. My correlation coefficient is 0 means my covariance has to be 0, right? So my covariance is 0 means they are uncorrelated, right? Uncorrelated doesn't imply independent, right? But for Gaussian, independent is uncorrelated. Uncorrelated is independent. That's the only case, and very important. So that's a good question. That's the only case when you get uncorrelated, you can see they are independent. Okay, just for Gaussian random variable. But general, when you get rho or your correlation covariance equals 0, doesn't mean they are independent. Because independent is if it's continuous, fx times fy equals the joint, right? This doesn't imply my covariance is 0. We can look at this. Still this one. This is your rho is 0, means they are uncorrelated. And actually, if you do the marginal, means I integrate through y or through x for this joint, you will get 2 parts, which both of them are Gaussian. And this is for mu1 sigma 1, this is for mu2 sigma 2. And if you times this to the product, you'll get this. So that's why you can derive for Gaussian random variable, uncorrelated is independent. Independent is uncorrelated. It's necessary and sufficient condition, right? If you know, I think you know the condition. Yep. Here's one example. Remember, the next formula is just so. what is the constant value C? Is that clear?
You should go with yes and see it.
Is it better? This is your power exponential part. Still remember? So you know the general formula like this, and this is, first you don't know, but I tell you this is a bivariate Gaussian random variable. Then you will try to map this to this, or map this to this, right? And you have, actually it's wrong here, is the minus 8x squared. I think it's plus here, yeah. So this 8, if I write this formula out, will be x squared over sigma x squared divide. So I have this move up, right? For the first item, this. Right? You agree? This is this part over this part over this, and the middle part is 2 cancelled, right? So x, y, 0x, 0, y, 1, 0 square, right? Am I right? This is 8 here. This is 18, yes, and this is 6. It's minus there, right? So that's very good. You will have this equals 1 over 4, right? And this equals 1 over 9. And you know this equals minus 6xy. So this gives you 0 over 3, right? After you get this, you'll be able to decide rho and sigma x, sigma y, okay? So when you notice it's a bivariate Gaussian random variable, or it satisfies this form, then you will be able to determine all the parameters, right? So it's a very nice problem. We have talked about the joint single random variable and joint random variable. So if it's multiple random variable, means you can have x, y, z, w, right? And you will have density function for each of them. Also, you'll be able to have density function as complex as those, right? So joint density function fxy is, if I draw it, the possible region is 2 dimension. So if it's fxyz, the possible region will be 3 dimension, right? Remember, I just talking about the region, not volume, not probability. Okay, so I'm still in density function. So if I integrate the three integral dx1, dx2, dx3, this is all the possible regions for x1, x2, x3. I will get probability distribution function, right? So same thing, you can have many, but it will be very complex if they don't have any relationship or they are very different from each other, right? So you just know we always calculate the nice formula or easy case, but it can be many different dimensions. You can have several random variables and think about the mix function of the several random variables. But another nice case is if your random variables, say n, you have 1 to n random variables, they're exactly same with each other. They have the same density function, same distribution function, same mean value, same variance, right? Just different name. We call it identical. If they are same, then they are identical. And independent with each other, mutually independent, means x1 is independent of x2 any through those. x2 is independent of any of those. So they are all independent with each other. Then we will have our nice properties. So we call those kind of distribution IID, independent, identically distributed. Okay? So IID is used a lot, maybe in your 600 or upper level class. Of course, they are identical, so mean value are the same, and usually we just use mu or mu x to represent that. And the variance is same, so you can use sigma x squared or sigma to represent that. Because they are independent, if you still remember, we know this. And we know this. Also, for continuous case, has to be density function here, right? So the joint density function is the product of all the density functions of each one, right? And an important function of your multiple random variables is sum. If I take sum of my random variables, start from 1 to n, call it Wn. Then the expected value of Wn is the sum of their expected values. You agree? First, expectation is what's called operation? Linear operation, yes. And variance. If I ask you variance of x, y, z, say x1, x2, x3, I think you know variance of x1, x2, so x1 plus x2 is variance of x1. If you still remember, when we talk about the concept of covariance, right? This is where your covariance comes from. x2. Remember? Right? So if there's sum of 3 random variables, it should be variance of x1, variance of x2, variance of x3, plus 2, 1, 2, 2, I will just use we. 1, 3, 2, 2, 3, right? Each other, right? You agree? So it's x1, x2, x3. How about this? This part is easy. How about this? For multiple random variable, you need to do this. This is for 5. And second step, third step, last step, it will give you exactly 10, which is to choose from 5. Because I choose 2. If I fix 1 is x1, then I need to have 4 different combinations. If I fix 2, I already have this, right? So just go this way. Right? And give you 10 for total. So this is, what does this mean here? You fix your I and your j is I plus 1 to n. Okay, for each I, your j is I plus 1 to n. It will look exactly like this. This is what we just, I don't know, I couldn't price. Okay, so we like the nice form. If they are uncorrelated, means your correlation is 0 for each pair. Then this item disappears. It's 0 there, right? So you have this. How about if they are independent? This or this? Independent. If they are mutually independent with each other.
Well, if it's counting,
Independent means, yeah, independent means uncorrelated, but uncorrelated doesn't mean independent, right? It's not applied everywhere, but true for Gaussian. So I'm asking you the easier case. I'm not asking you if they are uncorrelated, are they independent? I'm asking you if they are independent, then you know it has to be uncorrelated. So this 0, same thing, right? Yep. We did this before, and we just covered another 2 examples for this, right? So that's the sum of 2 random variable. Okay, we go to the how about we can take a break for 10 minutes, and then when we come back, we will finish the moment generating function and then do the quiz. Okay? So we'll stop at 8 today. So I will try to finish at 7:30. Sorry, 7:30, and then leave 30 minutes for your quiz. Okay? We'll have short.
go.
Yeah.
That's all it is. I'm not on the everything. Project probably. You guys just done Monday, didn't you? Oh, yeah. Well, I thought it was already. I thought it was we're planning on doing it Monday.
Oh, no, we were planning.
Just choosing a topic.
Yeah, so we think it was due for a while.
Yeah, and this wasn't there.
Yeah, us too.
Because no one at some point. Richard asked me today.
We had your number, Scott. We were looking for try to find one. Because I talked about like recent battery improvements. That's the only thing we can find, you know.
Yeah.
You try to look for stuff, but it's some technical in the next week, whatever time they try to really study to understand something.
Yeah, especially with new things. No, it's okay.
I'd rather like when the classes for trade something best.
Yeah.
Final draft.
Oh, yeah. We have to about that one.
So you pick you up 4 minutes. You gotta do that.
Yeah. We were doing that. We were like, something sexy. And I was asking, I was like, what do you want for this stuff? He's like, you see that text box? And I was like, hey, just in the text box. So I got a memo. So I was like, oh, okay, well, that money. So I copied and pasted my text box, threw in that text box, gave it to zero.
Good.
He said, yeah, the one that I knew off.
On the last one?
Yeah, so I think that's what copy and paste. But
That's what Josh had to say.
yeah, I mean, I asked him in person. But,
Oh, that's nice.
so yeah, there's some stuff.
Really good job. You actually do stuff for your project, like your body project.
No, especially now with what's coming up next week, I'll probably wait till next weekend.
guess just the battery. Yeah, but I'm sure like the battery is probably best just out. This guy had it last night. I had checked. Like even if I get nothing using my cash, you know, give me something. I can get like 2 pages just coming.
Oh, well, this is the second half of the report. Yeah. Right beyond we're doing this, we're basically making the LCD screens, and this one's more.
You guys do the exercise after post-test each time.
Yeah. Which exercise? What exercise?
The group.
Sometimes they come too late. Like a lot of times they're like 15 minutes before class.
Yeah, like they're never posted after we cover the material.
Yeah. Like if you could post them tonight so I could look at it, but yeah, you don't.
You have to do an exercise. For any probability central.
Yeah.
Pretty sure if you don't do exercise, maybe first test will be okay, but you'll never get this score in the following test. So just want to remind you, do the exercise.
So like only 5 was posted yesterday.
Yeah.
Well, you can start before it's posted, you know. If you stack on anyone, just skip. Try to do the easier ones first, and then do a little bit other ones. Because when you have done a few, several, you'll feel more comfortable to do a harder problem. But you can select those, you just want to point to the most important part. But I think you guys need a lot of exercise. Because I remember when I was studying this class, it's like after each day's lecture is 1 hour, a little bit more than 1 hour. I have to do like more than 10 problems. 1 hour more than 10 problems. So we do 3 hours one day. You think about that, you need to do how many problems to get comfortable. Or you just forgot everything. It's hard to follow the going to exercise.
So the exam will probably everything from chapter 7 will be on it.
Yeah, we almost covered everything in chapter 7. And we are talking chapter 9 now.
Is the final going to be comprehensive?
Well,
Is the final over the whole 6 weeks or just the last 2 weeks?
I think it's comprehensive, but I don't know focus on which part.
are we talking about chapter 8 at all?
We haven't.
But will we though? Is that,
We will.
okay. So do you think chapter 8 stuff will be able to pass?
You mean next? Dr. P will post the coverage this weekend on Friday night.
It's only whatever we cover up to today.
Well,
He will post
yeah.
the detailed coverage then
Try to see if you can do that before Monday. Because he likes to post stuff Monday before class about something Thursday. And it's like, it gives us 2 days to sort of.
We'll post this Friday night.
Okay. That'd be good.
Okay. Moment generating function. This concept is very useful because actually sometimes till now you're always given the probability density function or the distribution function. Means you know what kind of model exactly for that random variable. Then you can calculate all other properties like the expected value, the variance. That sometimes it's hard to get the probability density function, or you don't know what kind of model it is, but you have certain properties or certain features of this random variable. So it's like back forward. You can analyze the random variable by its properties. And this is a very good tool for that, the moment generating function. It is also actually called the characteristic function, but not in this book. If you take 600 and for communication higher level classes, it might be covered there. So this is a very useful tool. And actually it is a transform of your probability density function in the frequency domain. I don't know if you know signal and system, if you take basic class for signal system. Yeah. Okay, so you know Fourier transform, Laplace transform, right? Okay, great. So this is the definition. This is the definition. The moment generating function for random variable x is the expected value of e to the power sx. This s is the symbol in your Laplace transform. Okay? So you know that s equals j minus e to the j minus j omega. Right? Yeah.
So
So you still remember? Sorry?
Is it the same calculations as the Laplace transform?
Yeah.
So can you use Laplace transform tables?
Sorry?
Can you use Laplace transform tables to calculate?
You don't need to do that. Actually, just leave s there. You will see that. So this is the definition. It's expected value of e to sx is your moment generating function. If I write it out, you will know what is that. Because I'm doing expectation, so you know. For expectation, think about those as a function. Then I need my density function and my function, right? So why I say moment generating function, we can call it GMGF, is a transform of PDF, probability density function. This is in frequency domain because this is my PDF, right? And look at this. Right? So, did you remember if I use T, maybe you just easy to notice. That's Fourier transform, if I'm right. And Laplace is defining that as my S, right? Right? So this form is very nice because it's frequency transform of your PDF. Same definition. Expected value of E to Sx is actually just Laplace transform. So, and moment, so you call this function has to be a function of variable S, right? Because you are in the S domain. You can use this to analyze the signal or your communication message. So here we call it just random variable. So for certain random variable, if you get the moment generating function, you know, sometimes you know a lot about that random variable. So remember we have all the properties of our tensor model here. And actually, the moment generating function is also listed there with your mean and variance in the appendix. One way, why it is called moment generating function? Because, and I say it's a very useful tool, because you get, whenever you get the moment generating function, that means you're always, if you're solving a problem, maybe I just tell you the moment generating function, and I ask you certain other properties for those random variables. How can you do that? You first do the derivative of this, and then remember it's a function of variable s, so you need to do derivative for x, right? Did I say s or x? S here. And first do derivative, then takes, let x takes value 0. Don't substitute 0 into that immediately, then you get mistake. We'll try example and we'll see. If this have the second derivative, you will be able to have this. If this have the first derivative, we'll be able to have this. So you know that's the formula here. You do the nth derivative, it will give you the nth moment of that random variable. So using the moment generating function or the characteristic function, you can analyze that random variable. You can determine all the possible moments of that random variable. So if I have first moment, second moment, do I have the variance? Yes. So now you're very familiar with that, right? Let's do several examples. Remember, first do the derivative and then takes 0 for s. Takes, how about I will only do example for the model you know, and you can try more after class. This is discrete. Poisson is discrete model, right? And you know E of x is sigma, alpha, variance of x is alpha. It's easy to calculate this, right? This square variance is this equals something minus this. So that's why you have this, right? Now you know the answer, but if I give you this moment generating function, look like this: e to the alpha times e to the s minus 1. Remember, it's a function of s. If you know the moment generating function like this, can you find the first moment, second moment? And actually, when you get this, you know it's a Poisson. Because one way you will get this, it implies Poisson. Or you know this is the Laplace transform of your probability density function. So if you fix T, this MJ, moment generating function, then you know actually you fix the probability density function, right? So it's same thing. You give this or this. Actually, they imply each other. But we don't ask that way. I would just do the derivative of this and let's verify. Will that give me the first moment, second moment? I write it here to save some time. So I do derivative of this. Differentiation means I take this as one item because there's the e to s there. Or you can take this part as one part, right? It's a functional function. Then everything here remains the same. Derivative for this is this, right? And do derivative of this, you get e to s, because you are doing derivative for s. D function ds, right? See, this is my result after differentiation. And what I need, this is first time differentiation. So let s takes 0. The e to s will all give me 1, and 1 minus 1 here is 0. So this item give me 1. This 1 will give me alpha there, right? So this is e first moment of your random variable x is alpha. If I take the second derivative, means this is my first derivative. I need to do differentiation again, right? So use this here and do the differentiation. It's actually this part is 2 parts, can I call it uv, right? So derivative of this times this, derivative of this times this. Then it will give me this, and all the e to something. It's very nice when I substitute s with 0, 0 here, give me 1 here, give me 1 minus 1, 0, and this is 1, and this is 1, this is 1, 0, give me z to s 1, 1 minus 1, 0, and this give me 1. So will be alpha here, alpha square here, exactly as we saw here, right? So given moment generating function, you'll be able to calculate any moment, right? First moment, second moment, and you get second moment, you can calculate the variance, right? Another example, this is continuous. Given moment generating function, lambda over lambda minus s. Do the derivative of this fraction. Derivative of this, I assume you know. So remember, it's all for ds. So constant value 0, and this give me the 1, yes, so lambda here, and then this is my result. But next step, let s be 0. It will be lambda over lambda square, which is 1 over lambda. right? A very popular mistake is that has B0 there, then you get a totally different result, right? So first, to do the derivative, you need to have a function, and then calculate the function value when s equals 0, okay? So there's two examples. Actually, if you look at this appendix here, for all the models we know, the moment generating function is listed here. Okay, so you can verify. You're not required to derive those. You just need to be able to recognize. Okay, and actually those tables in exam is always public, right? Just give you those tables. Another usage for this moment generating function is when so just now we took the sum of multiple random variables, right? So remember, in the signal domain, if it's multiple random variable, you will have integration, right? Just think in general. But if I transform the signal to frequency domain, any convolution, why I have convolution? Because think, for example, w equals x plus x2, x1 plus x2. Then this is x1, x2. I will have x1, w minus x2. I think maybe, yeah, wx minus x1. This form, if they are independent, this equals 1x2, product of them. And this you can represent something like this. And this is something like this. So that reminds you convolution, right? Yeah, they are independent. We're talking independent. Actually, always for independent. To use this tool, okay. So this reminds me convolution. Right, you know convolution. So convolution in the signal domain means product in the frequency domain. Right? You learned that before, right? So that is why you see the moment generating function for a sum of multiple random variables is the product of each moment generating function. You will be able to derive or prove that, but it's not required. Another way to think about this, we know this is the definition of your moment generating function, right? Do I need to send later maybe? So if I want to know this, is product of your expectation, because they are independent. If x, y are independent, right? And look at one example, you'll be able to understand, right? Thus, for Poisson random variable, n Poisson random variable, call it k1 to kn, they are independent with each other, okay? So, independent, and the sum of those independent Poisson random variable is w. Then what's the moment generating function of your w? You know, for each Poisson random variable, just look at this. We just did this. It's e to alpha e s plus 1, right? This is moment generating function for a single Poisson random variable. And for that Poisson random variable, the alpha to differentiate with other, I just use alpha 1, right? First, the moment generating function is the product of those single moment generating functions. To n. And the E2, this is actually in page 316. And you can go through if you feel hard to remember this. I just calculate, and it's easy to simplify this. Give me another form which look very similar. If I call this alpha total, sorry about my writing. I don't know what I'm writing. We need to use here. This give me e alpha t times e to the s minus 1 here, right? This is still a Poisson, right? So that's the one proof seeing a sum of several independent Poisson random variable is still a Poisson distribution or still a Poisson random variable. And with the lambda equals alpha t, right? Actually, it's just the sum of all the alphas, right? So you have x1 with alpha 1, x2 with alpha 2, two different independent Poisson random variable, and the sum of them will be another Poisson random variable with alpha equals alpha 1 plus alpha 2, the sum of this parameter. Okay, it's very nice. So that is one usage of this moment generating function. You can use it to directly see this property, but it has many different ways to prove this property, and it's not required for this class. But you have to know is several Poisson random variable, they are independent. Then take the sum of this random variable, Poisson random variable, you will get another Poisson random variable, and the parameter alpha is the sum of those alphas. Or you think about in reality, some example like Poisson is trying to modeling the arrival problem within certain time, right? So if I fix the time interval, then if it's a bus stop, then or it's a parking lot, then the total car arrive within the certain time is a Poisson random variable. But actually, if I have like the green car, the arrival for the green car, the arrival for the yellow car, arrival for the red car, they are independent. There's no relationship between the arrival of a green car and a red card. They're independent Poisson random variable with different alpha. And if you know that, then you can model the sum of those random variables. Okay, so that's a nice form for Poisson. Actually, the Gaussian have a nice form too. I'll just basically introduce this. So for any random variable Gaussian independent, then the sum of that is also a Gaussian, but with the mean value n times mu. And the standard deviation is square root of n times sigma. So Poisson is listed here with parameter alpha, and you have several Poisson random variables. If they all have the parameter alpha, that means the sum of those independent Poisson will give you n alpha as the new alpha for your new random variable, right? And here, I link the Bernoulli to the binomial. So if you still remember, the Bernoulli is flip a coin, right? Just once, flip a coin. And the binomial is flip coin many times. If each time they're independent, and they're all Bernoulli, but independent, then the sum of it is a binomial. Okay? So this is the relationship. And here, the error and the exponential is also linked by the sum of random variables. So it's very nice property. And it's actually also represented in the table. I will stop here and give you the quiz. So we plan to end at 8. We will skip the first, the sub question C of the first problem. Okay? Skip this. And for the second problem, you're asked to calculate, first determine the constant A. I can draw the figure for you. See x less than y, you immediately, oh, sorry, it should be 45 degrees. So, 0 to 2, I will have this region, but y is greater or equal than x. Go that part, right? Y is greater, so you go that direction. So that's the possible area here, right? And the height of this area is constant A. A is a constant, it's not a variable. You know, you sum up all the possibilities should be 1. Means the area of this triangle and times A. So what's the area of this part? This is 2 here.
2.
Great. So, is that right? That's the height. Well, you can always do integration. Integrate like this or integrate like this. And you can verify. This is a tricky part, tricky method to decide A, right? Because it's a nice problem. So I can just look at the figure and guess A is 1/2. Okay? So
you need to do you're supposed to do your margin first. You're supposed to find your margin.
I don't know which part you are. So save some time while you use it for yourself. 1C, skip 1C and
There's bouncing defined as defining it as second squared or second.
Oh, this is sigma. Actually, usually when I say Gaussian, it's mu sigma. If I use normal, then it's mu sigma squared. So it's sigma equals 10. I have only one book here, so
Use no current copy.
Yeah, so then you work on copies. That's what it is, the last and all of the last was.
let me calculate, but I will first put this table here in case you don't have the book, okay? Let me check what value we need to look at. Okay. always remember Gaussian is symmetric for the expected value, right? So any problem related with expected value will have our next property. If you get confused, maybe you already did the first one, but if you get confused, just to clarify, those peak temperature, does that mean highest? It's many samples. Each sample, I call it a peak value. But that peak value has, the temperature has, this is mu equals 70, distribution like this. This is my t. For this part, my t is greater than 70. For this part, my t is less than 70. Every day I do a test, I do many, many tests, and it's a Gaussian distribution. Each one I call it peak value, peak temperature. It's just a word, peak temperature, it's just name, right? But like here, for example, this t has to be greater than 70, right? Think about your Gaussian distribution.
page is the table in the book? No, page 143. Excuse me.
if it's correct, then maybe I didn't check the number, but it's okay. So that's because I didn't say how to use this method. So then I have to
I think you got them, numbers. Do you just want us to find this out? You don't have to write the days or anything, right?
some maybe like
Only the first one?
maybe okay.
Okay, fine.
You did correctly that they asked us, and that's not same time if I ask
Yeah.
us, and that would be profitability with an entity. And in the same process, now it's two different questions.
Yeah, my question is, it's just, I know it's.
Written is something, you know those one,
Yeah,
and how about those?
I thought it was this one, I don't think that's the same as,
Yeah.
and that's what I'm missing out on, if I can't find the book.
There's a lot of examples that you might didn't pay attention, maybe you didn't pay attention to the direction. I can take you out more. But if you don't know, you know this part is very important thing. And you know this is correct for this. I mean, you just drop this.
I thought maybe I could take this approach on it, but.
Yes.
Okay.
But you did the wrong way.
Yeah.